Hi, I'm John. Welcome to my Electronics for Fun channel. I also have a website that ties in closely with this channel at electronicsforfun.com. Because I indicated that this channel was okay for kids, YouTube has turned off comments, but you can always go to the website if you want to post a comment. Previously, I made a video on series resistance and another one on resistors in parallel. This video talks about circuits that have both, combined, called a series parallel resistor circuit. Also included in this video is some information about conventional current, electron flow, and Kirchhoff's law. First, let's talk about which way current flows in a circuit. In 1750, Ben Franklin concluded, through some experiments, that what he called charge flowed. He didn't call it current, he called it charge. It flowed from a place of excess to a place that had too few. He ended up naming those positive and negative. And he wrote about this idea, and since he was a well-respected scientist, everybody thought that charge flowed from positive to negative. Like he said, nobody questioned it. Electrons had not yet been discovered. Later, a man named J.J. Thomson discovered electrons. That was in 1897, 147 years later. But by then, positive and negative theory had been printed in many, many books, thousands and thousands of books and diagrams, and millions of people were sold on Ben Franklin's idea. So the scientists all agreed, rather than reprinting everything, they just would call current conventional current flow, or simply current, even though they were wrong. But actually, the electrons flow out of the negative terminal of the battery, or other source, voltage source, through the circuit and back to the battery at the positive terminal. So we have conventional current flow, or just current flow, and we have electron flow. So somewhere in the middle between these two discoveries, in actually 1845, a physicist named Gustav Kirchhoff introduced a set of rules or laws dealing with current and voltages. This was before electrons were discovered, and so he used the conventional current flow method, even though at that time it wasn't called that because electrons hadn't been discovered yet. So Kirchhoff's laws can get complicated, like for example you can have multiple voltage sources and things like that, but for our purposes I'm going to simplify things. This shows Kirchhoff's current law, called KCL for short. What he is saying basically is that the total current entering a circuit junction is exactly equal to the total current leaving the same junction. So in this circuit example, I1, which is the current flowing out of the battery and through resistor R1, is equal to the combined current flowing through both R2 and R3. So I guess there were no electrons falling out all over the floor. Okay, so his KVL, Kirchhoff's voltage law, again oversimplified, says that for a closed loop series path, the algebraic sum of all the voltages equals 0. That's with the polarity of the battery reversed. So in this example, all that means is that the voltage drop across the resistors, when you add them up, would equal the battery voltage. Now here's our series parallel circuit we're going to be working with. Before we do our calculations, I want to point something out to you. Look at the schematic for a second. Okay, now look at this one. They look different, right? They're not. Here they are shown together. If you look at it close, you'll see that it's the exact same circuit. A circuit can be drawn in a different way and still be the same. Before we move on, take a look on the top diagram at resistors R2 and R3, which are in parallel. To do our calculations, we need to first find the total equivalent resistance of the whole circuit. Our first step would be to calculate the equivalent resistance of the combination of R2 and R3. In this case, they're both 10K or 10,000 ohms. If you don't remember how to solve for parallel resistors, you can watch my previous video or go to my website. But when parallel resistors are equal, like this one, both 10K, all you have to do is divide it by the number of resistors. Pretty simple. So 10K divided by 2 is 5K. And we're showing that here after redrawing the circuit. The equivalent of those two resistors is 5,000 ohms or 5K. Next we can see that the equivalent now would be just two resistors in series. The real 1K resistor and an equivalent resistance of 5K. And they're in series, and series resistors simply add together. So that is the equivalent of 6K. So now we know the equivalent of just one resistor is 6K. That means that those three resistors would present 6K, just like a 6K single resistor to the circuit. And once we know that, we can calculate the total current. Using our triangle, we see that I equals, which is current, equals V, which is voltage, divided by resistance, R. So V, we know, is 3 volts, and R is 6,000 ohms. So I'll divide 3 by 6,000, and that makes I, the current, come out to 0.0005 amps, which is 0.5 milliamps. Here's a little tip for you. Instead of all those zeros, if we have round numbers like in this case, we can just eliminate instead of saying 6K, we can just, instead of saying 6,000, we can just call that 6K, just 6. And then our answer is 0.5 milliamps instead of 0.00005, whatever. So it saves a little math, because you don't have to convert it back and forth. So now we know that the total current that comes out of the battery and goes through R1 is 0.5 mA. But when the current gets to the junction of R2 and R3, it divides according to their values. In this case, since they are the same value, the current splits evenly, and that gives us 0.25 through each resistor. R2 and R3 each have 0.25 milliamps flowing through them. And that also satisfies Kirchhoff's current law, because 0.25 mA and 0.25 mA equals 0.5 mA, which was the total. That's what's leaving the battery and returning to the battery after it goes through R1, 2, and 3. Next, now that we know the current, we can calculate the voltage across the resistors. We use our triangle again, but this time we're solving for voltage. We can see that V, voltage, equals I, current, times R, resistance. For R1, we get 0.5 mA times 1K, which is 0.5 volts, half a volt. For R2, we get V equals IR, which is V equals 0.25 mA times 10K, or 2.5 volts. In this case, R3 is equal to R2, and in parallel, so it'll also have 2.5 volts. Those are wired right across each other. So the voltage across R1 will be 0.5 volts, and the voltage across R2 and 3 will be 2.5 volts, for a total of 3 volts. Our battery pack consists of two 1.5 volt AA batteries for a total of 3 volts. 1.5 plus 1.5. According to Kirchhoff's voltage law, KVL, that is correct because the total voltage, 3 volts, is equal to the total of the voltage drop across R1 and the combination of R2 and 3. 3 volts. So that works. This next section shows a more complicated series parallel circuit. All I'm trying to show you here is how to get that total resistance, and we can calculate, once you have that, the current and resistance for everything else. I'll talk about that a little bit in a minute. So to solve the resistance equivalent for this circuit, we do it just like we did in the previous circuit. I find it easiest to start at the end furthest away from the source. So the first thing I would want to do is start at the right-hand side where you have R8 and R9, both 10K ohm resistors in parallel. We already know that we can just divide those by 2 because they're equal. Again, it gets more complicated if they're not equal, and I show a detailed description of that on my website and also on the previous video. So the 10K and 10K becomes a 5K equivalent resistance, and I'm showing that here. Next, we can see that R7 is in series with that 5K resistant equivalent, like that. And so series resistance, again, we just add them together. So we have a 5K and a 1K, and that works out to be 6K. Next, I'd go ahead and get those R4 and 5. Again, 2 resistors in parallel, piece of cake. They're 10K and 10K, so it would be 5K. Next, I would get a 5K and the 1K, R6, and that would be 5 plus 1, just simple, 6K. Now we have 2 6K resistors. 6K and 6K divided by 2 would be 3K. And at this point, we just have 4 resistors in series. Simple. Add them together. 3 and 1 and 1 and 1 is 6K. Now that we know the total resistance, we can calculate the current and voltage drops in the entire network of resistors. Remember, you can always pause the video while you look at the chart and let it sink in, and then hit resume when you're ready. The total resistance is going to be the current will be voltage divided by the resistance shown on the chart. The numbers on the left are the true values, and on the right I've shown where I've already divided the resistance by 1,000. We're going to be working backwards now to get back to our original circuit. This picture shows our 3 real resistors and 1 equivalent. Like before, we were shrinking it before, now we're expanding it back to the original spot. So each one of the real 1K resistors will have 0.5 volts, which is, we got that by multiplying 0.5 mA times 1K. So each of those will have 0.5 volts across it. The 3K equivalent resistor will have 0.5 mA times 3K, which is 1.5 volts. These values also prove the KVL, which was Kirchhoff's voltage law, because if we add the voltages across R1, 2, and 3, plus the 3K equivalent, we end up with 3 volts, which is the battery voltage in this case. Next, we break that 3K equivalent resistor back into 2 6K resistors in parallel. Here, we take that 0.5 mA, it splits in half. In this case, it splits evenly because our resistors are equal in value. From the chart, you can see that the current would be voltage divided by resistance, or 1.5 volts, which was we calculated in the last chart, divided by 6K, which would be 0.25 milliamps. Next, we split that first 6K resistor back into 2 resistors in series, a 5K and a 1K. The voltage drop across the 1K resistor, R6, is 0.25 mA times 1K, which is 0.25 volts. The voltage drop across the 5K equivalent resistor will be 0.25 mA times 5K, which is 1.25 volts. We split the equivalent 5K back into its original 2 resistors. R4 and R5 were each originally 10K in parallel. The current's going to split here like it did before. Each of those 2 resistors, R4 and R5, will have 1.25 volts divided by 10K, which equals 0.125 milliamps. The current through R6 would be 0.25 volts divided by 1K, giving us 0.25 milliamps. Now, the 0.25 milliamps through R6 is the total of both the current through both R4 and R5. They were 0.125 and 0.125, which is 0.25. But we've calculated it separately, but you can double check your work that way. That's one way you can check on yourself as you're doing these calculations. Next, we're going to look at that 6K resistor, the equivalent resistor, on the far right-hand end, and split it back into 1K ohm R7 and the 5K ohm equivalent resistor. The voltage drop across R7 is 0.25 milliamps times 1K, which is 0.25 volts. We're getting there. We're almost done. Bear with me. So the 5K equivalent would have a voltage drop of 0.25 milliamps times 5K, which is 1.25 volts. And finally, the 5K equivalent resistor on the end goes back to R8 and R9, each of which were originally 10K resistors. So we have two 10K resistors in parallel. The current through each of these resistors would be 0.25 milliamps divided by 2, or 0.125 milliamps. Notice we did things a little different this time, just to show you that since they're both the same, we didn't have to calculate each one individually. We could just divide, by 2. The voltage drop across each of them is going to be 0.125 milliamps times 10K, which equals 1.25 volts. That's pretty much it for this video. Don't forget, you can also go to the website at electronicsforfun.com. You can also reach me at electronicsforfun@aol.com. Subscribe if you'd like to. I hope to see you on my next video. Thanks. Bye.